Hello and welcome back to this series of tutorials, a course on learning Lean to create mathematical proofs. Just a reminder that it's a very introductory course. The idea is to kind of get us off the ground and get us confident with using Lean to write proofs. So it's not an advanced course. It's definitely aimed at getting over the initial barriers so that we are comfortable with Lean and the idea of writing proofs, simple proofs in Lean. So today we're going to be looking at our very first proof. Now before we dive in, I want to say that we are not expecting at all to learn Lean code today. The idea is just to take our first steps in writing a really simple, ultra simple mathematical proof in maths, plain English, and then seeing a Lean proof of that same kind of the same proof, and just making some initial observations about what a Lean proof looks like. So it's just a first look, so no expectation at all to learn anything about Lean commands and code. Not at all, not today. So it's just to kind of dip our toe and start becoming familiar. And I should say that we'll become familiar with Lean proofs and the things that Lean can do over time gradually. We're just building our familiarity. We're not expecting to learn something, see something once and know it inside out. Great, so let's crack on. So let's start with a really simple task, and you might chuckle at how simple it is. Imagine we've got a equals 4. That's simple enough idea. And our task is to prove that a is more than 1. Now you might have fallen out of your chair laughing at how easy that is. Clearly, if a is 4, it's more than 1. 4 is more than 1. And that is really easy, isn't it? But what we'll do today is to see how that easy, simple task can be written into a Lean proof. I think it's really important that we don't set ourselves overly difficult mathematical challenges while we're learning Lean, because that's a different skill. We're not learning here how to solve mathematical puzzles. The idea is how to create Lean proofs, so we don't want to add an extra distraction by having really challenging or difficult mathematical puzzlers. So this is really simple. And just for kind of completeness, we say that a, 4 and 1 are natural numbers. So how would we do this? And one of the challenges is that if we've got a really simple mathematical task, we kind of know it's true. Like if I said to you, a is 4 and that's more than 1, you'd probably agree, nod your head. You wouldn't need much more convincing than that. So one of the challenges we will face writing Lean, and that's kind of why I'm bringing it up, is being able to break things down, even if they're obvious and simple, into smaller proof steps. That's one of the things that we'll have to kind of do, so might as well start now. So the challenge is thinking about those easy steps in a structured way, and we'll kind of develop our practice over a series of videos in doing that. So how do we justify a is more than 1 if we're given a is 4? Well, the question really is 4 is more than 1, because we know that a is 4, so we want to justify 4 is more than 1. Now you might say, right, we can just stop there because 4 is more than 1. And in the last video, the introductory video, we did say that we can use generally accepted common truths in proofs, as long as they're not controversial. And 4 is more than 1 is probably right at that level. But because we're learning Lean, we do have to justify everything that we do. So let's just think a little bit about why is 4 more than 1. And if you think about it a little bit, or if you don't know, you can look it up. It depends on a property of the natural numbers. So the natural numbers are defined by the Peano axioms. And one of the things that we can do there is define the idea of addition. So 2 plus 2 is 4. And then we can define the idea of greater than, less than. So because 2 plus 2 is 4, we can say that 4 is more than 2. Let's a different example. 2 plus 3 is 5, and therefore we can say 5 is more than 2 and more than 3. So that's kind of how we construct some of those ideas of addition, and then greater than, less than. So we can give a reason. We can say A is 4. So this is our attempt at writing a structured proof. So A is 4. Why is A 4? If somebody argues with that, well, it's a given fact. It's given to us as part of the problem that we're trying to solve. And often that's important. That's a good habit to get into, writing down the given facts, the hypotheses sometimes they're called. So A is 4. Why? It's a given fact. You can see that we're having to be really thorough here, aren't we? And then we say this 4 is more than 1. Why? Again, we have to justify it. It's by the ordering of natural numbers, and that's what we were just talking about. The idea that the natural numbers have this concept of greater than, less than, greater than defined on them, and that's a property of the natural numbers. And then 4 is more than 1. So it's this, even though this might seem painful, I'm introducing it now because it's this kind of thinking, this setting out the given facts, the justifying every step. That's the kind of thinking that we'll have to get our brains doing as we write lean proofs. So it's good to start that with a very simple exercise. So this is the plain English mathematical proof. Let's see what a lean code proof might look like. And this is a real code. You'll be able to download this from GitHub and run it. Copy and paste it if you like into that website or into Visual Studio Code. And we'll just talk through at a high level, just make some observations about this proof. As I said, this is not about understanding all of it today at all. But having set out that challenge of proving A is more than 1, given A is 4, let's see if we can recognize some of that in this lean proof. So what can we see? Well, we can see this thing here, which says A is a natural number. So that's important, setting out what kind of objects we're dealing with. Yeah, that's nice to see, isn't it, in a lean proof? A declaration of the kinds of objects that we're dealing with. Are we dealing with rationals? Are we dealing with integers, reals, complex numbers, something else? So that's the end. By the way, lean code does use these actual symbols. So you'll have to find on your keyboard or input system how to enter the double stroke notation for the natural numbers. Once you've found it, it's easy to kind of reuse. What else do we recognize here? Well, we can recognize this thing, which is the thing we wanted to prove. So A is more than 1. That's the objective. So it's nice to see that's there. That's logical. It should be there somewhere, shouldn't it? What are we trying to prove? A is more than 1. So that's in there. What is this thing? Well, it says A is 4. That's what was given to us. It's a given fact. So I guess we're writing down given facts. And this thing, H1, well, we'll find out next time, but H1 is we've given this given fact a name, this hypothesis. We've given it a name so that we can refer to it later. So this is almost a statement of the theorem. The theorem being that if A is a natural number and A is 4, that's the hypothesis. If A is 4, then A is more than 1. Let's write that down using pen and paper. So A is a natural number. We're given A is 4. That's the theorem. That's the hypothesis. So if this is true, then A is more than 1. That's what we want to prove. If this is true, then this is true. So this is the hypothesis. I'm just explaining why it's called a hypothesis. Then this is true. So that's what our task really was. Let's go back to it. What else can we recognize in this code? We can recognize writing down A is 4. That was the first line of our structured approach to writing that proof. A is 4, we wrote down that fact. But this mentality of why justifying every line, we should do that. We need to do that here as well. So A is 4, why? There's some code here, I won't explain it today, but it refers to H1. So A is 4 because it's a given fact. We're told it's true. So that's probably what that does. In fact, that is what it does. And then we've got something that says, yep, it's more than 1. And how do we justify it? Well, we talked about the ordering on the natural numbers. So is that what that does? Well, it must do. Maybe we'll talk about that more next time. Maybe we'll say a few words about it now. So the idea is that we justify every line using this by and this kind of colon equals. So something is justified by something, and you'll see that in the proofs as a standard pattern. So if you want to download the slides for later reference, you'll just see a summary of what we've said. So the proof starts with a line stating the thing we want to prove with a declaration of what the variables are, whether they're natural numbers. The hypothesis is given as well. We happen to give it a name, H1, so we can refer to it. And then the statement we want to prove. And we also mentioned that actually this thing signals that the thing on the left is going to be proved by the thing on the right. Don't worry if you don't remember all of that. We will keep seeing it again and again. I mentioned something at the word example here. I'll just say something briefly about that, but again, we'll cover it again next time. This example, you might, lean proofs can have names. Lean theorems that you prove can have names. And they're named so you can refer to them later. But if you don't intend to do that, particularly if you're just proving a very small thing that doesn't require a long proof or a multi-part proof, then you can just call it example, and it just tells Lean that we don't really care about its name. You can call it anonymous, or if you're familiar with anonymous functions, it's kind of like that. So it's saying we don't really care about the name, we'll just call it example. So that's what that is. And then the last 3 lines of that proof, these 3 lines, are the actual proof of this theorem statement. We won't talk about that today. It's just setting up the strategy for the proof by calculation. So you probably worked it out already. We prove by calculating that 4 is more than 1. And then we have each line. So we set out the starting point. We want to prove something about A. That's there. And then we work our way step by step to the conclusion, and each step has to be justified by either logic or some other reason that we all commonly agree is valid, called tactics. So you'll see that word tactics quite a lot. So each of these lines, the progression to the next line, is justified by a tactic. So 4 is more than 1 is justified by this tactic, and then we'll talk a little bit more about what that is. Let's actually do that now. I'd forgotten we were meant to cover it today. So we justified 4 is more than 1 with that norm num tactic, that thing that justifies that. So how did that happen? Well, we've already said you could do it by going all the way back to the Peano axioms and defining addition and then greater than and proving it deeply and thoroughly like that. But actually, as I said, most practical everyday proofs, you don't have to go all the way back to the beginning. Our attempt at a maths proof here didn't do that. We didn't go all the way back to the Peano axioms, and we don't need to do that with Lean proofs either. We use or reuse commonly accepted fundamental results, like the square root of a real number is positive, that kind of thing. And the idea that, say, 3 is more than 1 and 4 is more than 2, it would be really painful if we had to prove that every time we used it. But we still have to justify it, so we do have to say why that's true. And in our minds, it was true because we're saying there's an ordering on the natural numbers, and 4 is greater than 1. So Lean has this library called MathLib, and in that, growing over time, is an increasing number of fundamental results and methods for helping us write proofs without going all the way back to the basics. So we refer to the tactic that helps us prove and justify 4 is more than 1. So that's what that norm num was. Let's point it in the code. There, that's what this is. This is a tactic, and it's how we can justify that 4 is more than 1, and it comes from the Mathlib tactics library. So I'll stop there, and just to conclude there. So today we looked at a very simple mathematics challenge. Let's go back to it. The challenge was A is 4, prove that A is more than 1. We did a lot of thinking about why that's true, even though it sounds really obvious. We tried to structure our thinking, and we kind of wrote a very simple 2-line proof, and we did add some structure. We sort of said A is 4, it's a given fact, it's more than 1, and we thought a bit deeply about why that's true. And it's just a property of the natural numbers. There's an ordering. This thing is an ordering, and then we use that insight, that kind of discussion, to help us write a lean proof, which makes use of that. So those concepts from the English proof, plain English proof, translate over into the lean proof. So we set up our object types, we define the given facts, we set out what the objective is, the overall objective of the proof, and then we use what we're given, and we justify it. We move on to the next line, which happens to be the conclusion, but it might not be. We might have several lines, but each line has to be justified, and we'll see lots of justifications over time. There's lots of interesting things we can use, but those are called tactics. Great. So hopefully that was an interesting first look at lean. As I repeat, you don't worry if you aren't familiar with lean code. The idea today was not to learn any of it, but just to see the parallels there and get our first look. Now, as you know, you often learn by doing, and at the end of each of these videos I'll have a very, very simple exercise. And as I said, the idea is not to set a devilishly difficult mathematical challenge. I'm going to choose really easy mathematical challenges because I want us to focus on practicing using lean. So, without getting distracted by the difficulty of the mathematics, let's make sure that we've understood and used the lean concept that we're introducing. So all the exercises will be easy exercises in that sense. So we've got a lean program that proves A is more than 1, given A is 4. Now, can you take that code, copy and paste it, download it, and prove that A is less than 10, given A is 4? So you won't have to write up code from scratch. You can take that one and just modify it. So A is 4 is given, so you probably won't need to change that bit of the code, but we probably need to change this bit which says A is more than 1. We want to prove A is less than 10. And a tip is that norm num tactic, that body of knowledge that's inside the lean Mathlib library, we've shown that it understands greater than. It's what justified 4 is more than 1. It also understands lots of other things that we haven't covered today, including less than. So you can see that will be useful for doing this. So have a go at that. As I said, these are designed to be easy exercises, so the mathematics won't be the challenge. The challenge will be just practicing using lean. So have a go at that. Any questions, do reply in the comments, and we'll have a discussion there. See you soon. Bye.